Hi everyone, today I'm going to be talking about the effects of foveation on deep neural networks as a way to explore the role of foveation in humans. So one of the main differences between human and machine vision is the fact that machines have spatial uniform processing over an image, while humans perceive the world in a spatially varying way. This phenomenon is known as foveation, and by this I mean we perceive with high spatial acuity at our center of gaze, which is the fovea, and with lower spatial resolution in the periphery, where the percept seems somewhat distorted or scrambled. Now, till date, it's been debated whether our foveated visual system was designed this way to optimize for metabolic cost, so to be efficient because you only have a finite amount of photoreceptors in the retina that can relay information to the optic tract to the LGN, or arguments about functionality. Maybe you can achieve higher levels of robustness or invariance by learning to see through the somewhat distorted visual representation. Now we're going to test this hypothesis by doing the following. We're going to introduce foveated perceptual systems, which are two-stage systems that consist first of a foveation stage, second by a CNN that must perform scene classification. In particular, we're going to use a metamer transform for our foveation procedure that locally perturbs in each one of these log polar receptive fields the image in the direction of its local texture statistic up until it renders a visual metamer. And this metamer transfer model was inspired by the Freeman and Simoncelli metamer model from 2011. Going back to our main conditions, foveation net is foveated, standard net is non-foveated, foveation ognet is foveated and has eye movements, and standard ognet is non-foveated, yet the data is augmented with random recropping and horizontal mirroring. Now, once we've defined these four systems, what we're going to do is we're going to perceptually evaluate each network and see what we can find. What do I mean by that? We're going to train each one of these networks 10 times, randomly initialized from matched noise seeds. And we're going to test the foveated perceptual systems on foveated images and non-foveated perceptual systems on non-foveated images. And in doing so, we'll find that their scene classification performance, also known as generalization in machine learning, is all about the same for each one of these 10 noise runs. However, when we flip the visual stimulus and show non-foveated images to the foveated systems and foveated images to the non-foveated systems, the drop in performance is higher for the non-foveated systems converse to the foveated systems. So this would imply that foveation nets have higher cross-generalization than standard nets. Now, why is this the case? Let's keep digging into this question. We wanted to occlude the stimuli from the outside in, the glaucoma condition, and inside out, the scotoma condition, and test each one of these systems. And we find that foveation net and foveation ognet are highly more robust than standard net and standard ognet for scotoma-like occlusion, although we only find a marginal effect for the augmented invariance in the glaucoma occlusion. And a closer inspection of why this is the case, we find that it's the foveation transform that will change the visual area for the second stage of the perceptual system. So maybe this difference in the visual area is what's buying us our robustness to occlusion. So to do that, we're going to rerun our experiment where we're going to occlude the visual stimulus after the foveation stage. And in doing so, we find that this robustness to scotomal occlusion, interestingly enough, goes away. From here, we can conclude that robustness to scotomal occlusion stems from the foveation procedure itself, not by the texture statistics in the periphery. However, the story doesn't end there. We wanted to see if there's a center image bias for each one of our systems. So we rendered Q-conflicting stimuli that were windowed, giving the area and size of each one of these log polar receptive fields. And the stimulus looked like this for the foveated perceptual systems and the non-foveated perceptual systems. We wanted to see the bias of each one of these systems towards these stimuli as we increase the ratio of central image area with the foveal class. And we noticed that non-foveated systems actually perform better than foveated systems, which means that they're less biased to the Q-conflicting information in the fovea. And if we flip that test the other way around, we do find the opposite, where foveated systems are more biased to this Q-conflicting stimuli than non-foveated systems when they have to perform accuracy for the foveated class. So from here, if we localize a point of selective equality for each one of these perceptual systems, we can conclude that foveation nets are more biased than standard nets to central image regions because they need less foveal area to arrive to the same point of subjective equality. The final experiment we ran had to do with spatial frequency sensitivity, because it's natural to imagine that maybe foveated perceptual systems are more robust to low pass frequency information. Surprisingly, we find the opposite, that Foveation nets are less sensitive than center nets to low spatial frequency information. And this effect is flipped nominally for a high pass spatial frequency stimuli. So overall, we find that our results are amplified for the augmented variance of each one of these systems. So if we do Foveation net versus standard net, however, comparing Foveation net versus Foveation net, eye movements don't buy you anything. There's no perceptual difference whatsoever. But there is lower cross-generalization, lower robustness, and higher sensitivity biases between center net and centered augmentation net. And in particular, I want to emphasize the effect that Foveation induces a central focusing mechanism on the visual stimuli. And it's not the texture statistics themselves. They're implicitly giving you that focusing mechanism at the center. And future work is going to explore the effects on training on objects versus training on scenes. For more information, please see our recently submitted NERVS paper, Emergent Properties of Foveated Perceptual Systems. Thank you.